Hello, welcome back to my lecture presentation on Chapter 4, Subtopic 4.4, Intermolecular Forces. In this video, I'll start off by refreshing back about what you had learned in the first video, that is the intermolecular van der Waals forces. After which, I will continue with the second type of intermolecular forces, that is the hydrogen bonding. In this slide, I am putting down the two types of van der Waals forces together, side by side, the London forces between non-polar molecules and the dipole-dipole forces between polar molecules. Each type together with diagrams illustrating on how the forces arise. Taking a close inspection on the diagram for non-polar molecules, you are able to see that the broken lines in between the molecules are actually the attraction between the opposite charges. The partial negative end of one molecule attracts the partial positive end of another neighboring molecule. Yeah, this part. Similarly, for polar molecules, the broken line between two molecules is also due to the opposite charges attracting one another. Partial negative end of one molecule attracts the partial plus end of another neighboring molecule. So this is the similarity between London forces and dipole-dipole forces. Generally, they are opposite charges attraction. Back to the non-polar molecule, the vector arrow on the molecule, which denote the molecular dipole, is a temporary dipole or induced dipole. Whereas for polar molecule, the vector arrow on the molecule denote the permanent dipole. Which means that the force of attraction between permanent dipole molecules are of course stronger compared to the force of attraction between temporary and induced dipole for non-polar molecules. So generally speaking, dipole-dipole forces are stronger than London forces between non-polar molecules. And for polar molecules, they have different degree of polarity. The more polar the molecule, the stronger the dipole-dipole interaction. There are three factors influencing the strength of van der Waals forces. First, molecular mass or molecular size. Mass and size are actually related. When a molecule has higher mass, so the size is also larger. A larger molecule has stronger van der Waals forces. This is because when the size of the molecule is large, the surface area of the molecule is also large. So when one molecule is in close proximity with a neighboring molecule, the attraction between them would be stronger. Second, molecular polarity. Polar molecule has both dipole-dipole and London forces, compared to non-polar molecule which has only London forces. Therefore, the intermolecular van der Waals forces for polar molecules are stronger compared to non-polar molecules. But when the molecular mass of one molecule is so much higher, yeah, could be double or triple, yeah, the mass of another given molecule, the polarity factor would be insignificant. Yeah, bear in mind that. So every time what you need to inspect is the molecular mass. Then followed by molecular polarity to figure out which factor outweighs, yeah, the influence on the strength of van der Waals forces. Third, molecular shape. Molecular shape factor is prevalent only when we are discussing about molecules which has more atoms or polyatomic molecules. This is especially applicable to organic compounds. Take for example butane. Yeah? Most organic compounds have isomers. Butane has two isomers, a straight chain molecule and a branch molecule. So comparing the shape, yeah, between a straight chain and a branch molecule, straight chain molecule has larger surface area. Therefore, the intermolecular van der Waals forces are stronger. This slide summarizes the van der Waals forces that we had discussed. Dipole-dipole forces and London forces. Dipole-dipole forces exist only between polar molecules, whereas London forces may exist between non-polar molecules as well as polar molecules. And below is the summary of the factors influencing the strength of van der Waals forces that we had just discussed in the previous slide. Well, this slide is a quick exercise just to test whether you have understood what has been delivered so far in the lesson. State the type or types of intermolecular forces that exist between each of the following molecules. So you are given three molecules, H-Br, hydrogen bromide, sulfur dioxide, SO2, and methane, CH4. As a guide, the first thing you need to find out is whether the given molecule is polar or non-polar. HBr. HBr is a polar molecule. A polar molecule has dipole-dipole forces as well as London forces. The second, SO2 or sulfur dioxide. Previously, you have learned, yeah, to predict polarity of molecule, and I suppose SO2 is one of the molecules that you have dealt with before. Yeah, SO2 is is also a polar molecule. So polar molecule has dipole-dipole as well as London forces. The last, methane molecule. Methane is a non-polar molecule. So the only intermolecular forces exist is London forces. In this slide, we will be discussing about hydrogen bonding. Definition. Hydrogen bonding is a special dipole-dipole interaction between the hydrogen atom in a polar bond, particularly NH, OH or FH bond, and an electronegative atom, nitrogen, oxygen or fluorine, of another nearby molecule. The requirement for hydrogen bonding is, first, the molecule must have NH, OH or FH bond in it. Second, neighboring molecule has nitrogen, oxygen or fluorine atom. The factors affecting the strength of hydrogen bonding. First, the electronegativity of atom. And second, the number of hydrogen bonds present. These are examples of molecules that are able to form hydrogen bond between molecules. The first, hydrogen fluoride, HF. Since there is a HF bond in hydrogen fluoride, so this molecule fulfills the requirement for hydrogen bonding. The second, H2O, water. Water has OH bond in it, so it also fulfills the requirement for hydrogen bonding. Third, ammonia. Ammonia has NH bond in it. Again, this molecule fulfills the requirement for hydrogen bonding. For water and ammonia molecule, each molecule may form more than one hydrogen bond with the neighboring molecules. And comparing these three molecules of HF, H2O and ammonia, the hydrogen bond between HF molecule would be stronger compared to the hydrogen bond between H2O molecules, taking into account the electronegativity of the atom, where fluorine is more electronegative than oxygen. And oxygen is supposedly to be more electronegative than nitrogen atom. Therefore, the hydrogen bond between ammonia molecule is expected to be weaker than those between water molecules. The energies of hydrogen bonds vary from about 4 to 25 kJ per mole, which is on the average above 10%, about 10% the strength of a covalent bond. So this means that hydrogen bond is weaker compared to a covalent bond. The bond energies of FH, OH, and NH are shown here respectively, which are 567, 463, and 391 kilojoule per mole. Since the electronegativity of fluorine is higher than that of O, oxygen, and nitrogen, so the hydrogen bond formed by FH is much stronger compared to OH, and OH stronger than NH. So this is how electronegativity of atom influence the strength of the hydrogen bond. This slide shows the effect of hydrogen bonding. There are 4 effects. The first, the effect on the boiling points of hydrides of group 15, 16, and 17. Second, the density of ice in comparison to water. Third, the dimerization of carboxylic acid. And fourth, the solubility of compounds in water. So these effects will be discussed as application in the tutorial class. Thank you.